Welcome to Ask and Learn.
Okay, so in this problem, we're talking about expanding a gas, or excuse me, heating a gas in two different ways. One, you let the container expand. One, you force the container to stay the same size. And the questions are, how much heat is required for each of these processes, and what do we make of this? So they start off with what happens if the volume stays the same. And so if the volume stays the same, what's the heat? Well, to find heat for an ideal gas, you generally want to go to this formula. The delta U is Q minus the work done by the gas. In this case, this term is zero because work is the area under the curve for a PV diagram, and the area is zero if the change in volume is zero. So Q is just going to be the change in internal energy, and that's just going to be NCV times T final minus T initial. So if you plug in 67 and 27 and 0.01 and 12.47 joule per mole Kelvin, which I found in the book, it's in a table in the book, perhaps you will get what I get, which is 5 joules. Oh, let's get that J looking good. Okay, great. And so next, what happens if you do this, but you allow the gas to expand, but you keep it at a constant pressure? So to do this, again, we want to use the approach of delta U is Q minus the work done by the gas. And then you want to say that Q is equal to delta U plus the work done. I have to write slower, I guess. The work done by the gas. And delta U, okay, actually, yeah, so let's draw a PV diagram to aid us as the problem suggests we do. So we have your initial volume and then your final volume. And you just kind of go like this. So to find the work, we need to get the area under this curve, and I'll go ahead and color it a different color. Oh. So this area. So to do that, what we need to do is get a formula for the final pressure. So I'll kind of put dotted lines. Oh, it didn't change color, but that's okay. So we want to get the P final, at least a formula for it. Oh, I'm sorry. The V final. We need a formula for V final because P stays the same. So V final equals question mark. So you want to figure out V final by using PV as nRT. And then P stays the same, nR stays the same. So you can say P divided by nR is equal to V initial over T initial equals V final over T final, because right, P over nR always stays the same. And it's always equal to V over T. And therefore, you get that V final equals T final over T initial times V initial. Great. And we want to evaluate the quantity PV, or PV2 minus V final minus V initial. So PV to get the work, because it's just the area of a rectangle, and the rectangle's width is V final minus V initial, and its height is P. So V final minus V initial. And if we just go ahead and plug in things that we've calculated, I'm gonna like kind of dot that to show like it's like its own little thing. Okay, equals P times V final, which is T final over T initial minus V initial. Oh, excuse me. That's got to be times V initial minus V initial. Okay, and I had a nifty way of thinking about this because let's see, we know T final and T initial, but we don't really know V initial, but of course we can write a formula for it. And so I'm gonna like do this on the same page. Sorry, it's gonna get like slightly messy, but I think it would be easier to at least see the algebra. So we're gonna move kind of this way. Okay, so V initial from PV equals nRT is nRT initial divided by P. So if you take this, I'll do this in a different color, and then you plug it into here. It's just going to be algebra from here on out, but it'll be nice because it comes out really simple. Then you get P delta V, that's delta V, is equal to P times T final over T initial times nRT initial over P. Can you see the cancellations? Times nRT initial over P. And then now you can see that like lots of stuff cancels. It becomes super simple. Be able to make some nice comments at the end of the problem. So if you distribute that P, then it cancels and you're just left with nRT final minus T initial, which is the same thing as delta U was in the case that there was no work done. And so I'm just gonna then to kind of summarize, and I'll just do this summary on the next page, that the work is equal just to 2 NCV delta T, and we already found this in the last problem, which was 5 joules. At least that's what I calculated. So you get that the work is 10 joules. Okay, now the best part. I'm just gonna talk about this. So where does the extra energy go? So in one case, you're keeping the volume the same. One case, you're letting the volume increase. So the extra energy goes in the energy needed to expand the the energy needed to expand the walls of the system and by keeping it at a constant volume. So it's literally like work is force times distance, the force needed to expand the container, all the while keeping the pressure constant. So it's not like you could just like increase the volumes all of a sudden or something and be like, well, the gas didn't really do that work. If you're working under the constraint that the pressure is constant, I think it's the case that the gas has to be the sort of pusher of the container. And so on a microscopic level, each like atom is losing energy because it's moving an atom in the container. So what else is asked? So find the final. No, that's not it. And then it asks for the change in internal energy. So the change in internal energy we saw in the last one was 5 joules. So for part A, actually, I guess I'll label this for D. I just kind of talked out what the answer is for D. So for A, delta U was 5 joules. And then for B, the delta U, it was also 5 joules. and that reflects the fact that the final and initial temperatures are the same, and then U is a state dependent, particularly depends on the state of the temperature, and so that's why they have the same change in internal energy. And let me double check. Is there anything else? Yeah, I think that's it.